stop sharing that's what it does. It just does it to drive me crazy, that's all. So at the end of class last time, I was talking about why do reactions happen at all if the activation energy is much greater than RT. And remember, I talked about how EA, well, we knew this from general chemistry, is the needed energy for a reaction. It's the energy to go over that barrier, right? And RT, I introduced RT, or KT if it's one molecule, as the available energy. So it's like the thermal motion energy. You can think of it as the kinetic energy of those moving particles. So if the activation energy is a lot bigger than the available energy, why do reactions happen at all? And the answer to that, I think, is you're always going to have your above average molecules. So some molecules are above average. And in other words, they would be moving with greater speeds, and they would have the kinetic energy needed to go over the barrier. So some fraction of molecules will have the needed energy. They'll be moving fast enough, or, you know, that's saying the same thing. But if you wanted to, let's say, suppose you wanted to get at what is the fraction, supposing you're really interested in the rate of that reaction, and suppose you want to know, you know, what fraction, you figure out that they have to be moving at 500 meters per second to have the right energy to go over the barrier. It's kind of silly, but suppose you want to know what fraction of molecules in this sample at this temperature move with a speed of, I don't know, greater than 200 meters per second, or whatever speed you decide. And, you know, we know what the root mean square speed is. We know it's the square root of 3RT divided by the molar mass. But there is no way that knowing this average will be able to get you this kind of detailed information. So you can't get this information from an average. An average is really a limited information. And this is where I think I ended the class last time. So what we need is deeper information than that. And what we really need is to know what is the speed distribution in the sample. This is what we want. Okay. So, you know, actually that lab lecture 1, I talk a little bit about distribution functions there. And one reason I do that is usually I give that at the beginning of class, and it gives people some background for even this unit. You know, there's distribution functions are all over physical chemistry. So what we want is the speed distribution function. So in general, and I'm sure there's some of you in here who've taken statistics, but not everyone. A distribution function is the probability of a certain population having a certain value of a property okay? So for example, a height distribution would be the probability of a certain height among, you know, United States males or something like that. And you would have the probability of a certain height as a function of height or something like that. So this is a pretty typical distribution function. This is the probability of having a certain, like h, certain height as a function of height. It says I talked about it in lab lecture 1, but this year I didn't quite do it that way, but it is talked about it there. I use the same slides even. And you know, this is your tip, this is your bell-shaped curve. Okay, and right in the middle here, you have your most probable height, right? And you also, that also is the average height, because you basically have equal areas, equal probabilities on both sides of the average height. So it's very symmetrical, and that's very nice. How do you get such a curve? Well, you'd have to do a whole bunch of measurements, okay? You could go out there and you could measure the heights of a certain fraction of the population. Then you would calculate the fraction at each height. Now, and if you do a few measurements, you'd have kind of a messy looking curve. All right, this is kind of messy looking because you didn't do too many. But as you do more measurements, that curve looks nicer and nicer. But I want to point something out because it's a little different from the speed distribution that we talk about, we're going to be talking about. And that is that this is what is called a discrete distribution. And that is to say that heights are grouped in certain small intervals, okay? So for example, you might have inch intervals, and you know, you have the fraction of population between 5'9" and 5'10", between 5'10" and 5'11", that sort of thing. So that's a discrete distribution. Okay, so this is going to seem like real basic and silly stuff, but I'm going to be talking about this with the speed distribution. So I want to make sure that everyone's on the same page here. So I want to talk about how, you know, knowing the distribution function, well, it allows us to calculate some really cool things like a fraction above a certain speed, but knowing the distribution function also allows us to calculate averages, the average, okay? So like, for example, how do you calculate an average height? And this is going to look kind of silly, but what the heck? What you do when you calculate a height, an average height, is you know, you have, let's say you have 6 people, and their heights, I'm just going to put them in inches. I have 2 at 72, 72, 72, 73, 64, oh God, 64 and 62. So those are the heights of the people in the room. So to find the average height, you would add them up and divide by the number n, which is 6. So you would take and find your average height would be 72 plus 72, 73, 64. Everybody knows how to do this. And then you divide that by 6. Or you could do this. You could say, okay, there's 2 at 72 and 1 at 73 and 1 at 6 and 2 at 64 inches and 1 at 62. This is the same thing divided by 6. But so you could also think about this as, so this is the number of people at the ith height times that ith height. So this would be n1, where that one index is at 72 inches. And then you would divide that by, and you'd have to sum this. And then you divide it by the total. Okay, so that is the average height. But what you could also do, you could see that this same thing could be 2/6 times 72, right? All I'm doing is multiplying it out, plus 1/6 times 73, plus 2/6 times 64, plus 1/6 times 62. So how is this, how would I write that? Well, this is the fraction at 72 inches. This is the fraction at 73 inches. So what I'm doing here is I'm saying that the average height could also be thought of as the sum of the fractions at each height times that corresponding height, right? So Fi is the fraction at height I, and Hi is height I, and you would sum over all the heights. So these are really the same thing. Now, when you have a large population, then you don't calculate fractions anymore. You call them probabilities. You think that, so you end up with the probability at each height. So this fraction becomes a probability. So you would say that the average height is the sum of Pi Hi. So here it's exactly the same thing as what we just figured out. And I want to point out that, again, this is for a discrete distribution. Okay, let's say that you have 1-inch intervals for these heights. But there are lots of distributions. In fact, the speed distribution that we're talking about, there are also continuous distributions. Okay, and for a continuous distribution, you can no longer calculate an average by doing a sum, because if you have infinitely, if you have those intervals get smaller and smaller and smaller, now you're doing an infinite sum, right? You'd need an infinite sum. So what do we do instead? An infinite sum. The sum becomes an integral. So that this Pi becomes the probability at a certain height, like as a function of height, okay? So that the average height would be the integral of P of H times H dH, right? So we had the sum of Pi Hi, but that becomes an integral, see? So it looks very much like it. And of course, it has to be integrated over the entire range of heights. So, to make sure you don't leave anyone out, you can integrate from 0 to infinity. And a lot of times that's what you do, because that's the easiest limits to use with a lot of these functions. So going back to how we calculated the average height, suppose we didn't want to know what the average of the height was. Suppose we want to know what the average of the square of the height was, right? So if you go back, what we would do is we would have squared the heights here, right? We would have had 26 times 72 squared, right? So that would mean that we'd have an H squared in here. So if we want to find the average of any function of height, it's just the integral of PH times that function. So if we want to find the average height squared, that's the integral of P of H squared dH. We want to find the, any other thing, that's what you'd have to do. If you wanted the average of 1 over the height, it would be the integral of P of H, 1 over H dH. Anyway, that's kind of a silly example, but so for a speed distribution, so we have the average speed, you would take the probability of having a certain speed times that speed. I actually usually write it the other way. I put the speed first. I don't know, it's just a convention I use. Then you would integrate that from 0 to infinity. If you wanted the average of the square, okay. Now, what if you wanted the root mean square speed? Now, let's remember now, the root mean square speed is the square root of the average v squared. Is that the same as v? Is that the same as the average V? It's not. No. Yeah. So what you would have to do if you wanted the root mean square speed, it would actually be the square root of this whole thing. Which frankly, after you do this integral, you get, you know, a bunch of constants, and then you just take the square root of it. So it's not really hard. But if you're asked to do that, please don't tell me that's just V average, because it's not. It's a different quantity entirely. Okay, so in fact, we actually know, right? We know what the root mean square speed is. We know it's the square root of 3 RT over M. And that, like I said, that's the square root of V squared. So that means that the average V squared is 3 RT over M. and that is the integral of V squared, because that's the function of V we want the average of, P of V dV. So this, believe it or not, is one way of figuring out what this function is, because we know that when you integrate V squared times it over all 0 to infinity, you get this answer. So then we could figure out what that function should be. And that's a great job for a mathematician, not for a chemist. Okay, so we're not going to do that. We're not going to figure out what P of V is from that. Instead, we're just going to use what the mathematicians found out, and they came up with that. Well, this is the answer. This is what P of V is, but it's called F. For some reason, they like, this is what's normally used, as we use an F instead of a P. I don't know why. But it's got a bunch of constants. It's got a V squared in it. That's not this V squared. That's part of, it's part of this probability, right? It's part of P of V. Okay. And look, we actually have a molar mass times V squared. Look at that. That's like a momentum. That's like an energy over something with an RT. So here again, we're sort of comparing energy to RT. You're seeing another example of this. Like I told you, is all over pChem. So this is what we call the Maxwell-Boltzmann distribution of molecular speeds. Okay. And it is not a bell curve, right? A bell curve would be just this part, right? A bell curve is e to the minus AV squared, and it looks completely symmetrical. This is not a bell curve because it's got this V squared here. And that changes its shape, makes it a skewed bell curve. So it goes up. So if I were to draw a bell curve here, this curve rises more quickly and decays more slowly, something like that. I don't know if I draw that too well, but I don't know. You know what? I just want to show it to you. I don't want to. Sort of like that, okay? So this is the Maxwell-Boltzmann, and this is your bell curve. Okay, so it has a different look to it. And I have a little slide here of it, but it almost looks symmetrical. But look at this. I gave you this, but I changed the scale. It was like 1, 2, 3, 4, and those were ridiculous speeds for molecules. So I just multiplied everything by 100. So I changed the units. So you could see that if it was symmetrical, it looks like the maximum is at 100, then this would come down to 200, right? Because 0 and 100 would come back down to 200. But you can see it's a little skewed. It's lifted up. It's not down completely at 200. So this is, well, I guess there's no pi in there. Wow. This did not reproduce very well. Wow. I didn't notice that. Well, anyway, I fixed it. So, so, you know, what if we wanted to know, you know, what is the fraction of molecules moving greater than 200 meters per second? What you could do is find this area here, which would actually be the integral from 200 to infinity of f of v dv. So you wouldn't put a v squared in there because you're just finding the area under this curve. Okay, so that's how you could find that. And this integral, by the way, there are tables. It's very easy to evaluate it. You can't evaluate it that easily analytically, but you know, it's known very, very well. So let me ask you something else. So just, you know, what would be the area under this curve? So you know what the area under that curve would be, right? Because basically it's the sum of all the probabilities of being any speed. And those have to add up to 1. Because in a sample of molecules, they have to be moving with a speed, okay? So you sum them all up, and so the area is 1. So we can look at how these curves change with temperature. Again, they're looking a little too symmetrical to me, but that's okay. I got them out of a book. But I want to look at the lower temperature, which is the green curve, and the higher temperature, which is the orange curve. So the first thing you notice is that, you know, most of the molecules at the lower temperature are moving with speeds like in here. So they're moving, you know, they have average speeds that are higher. So there's a higher average speeds at a higher temperature. Because here it would be here. Those are all higher at the higher temperature. Another thing you notice is that you have a greater range of speeds at a higher temperature. So you could see if you look at like the full width at half maximum, so go down to the top halfway, you could see that you might have a much wider range here, okay? And actually, that's why the curve flattens, because both of these have to have areas under the curve that equal 1. So if you have a wider range, you have to have a lower top in order to have them all equal the same thing, 1. And then I just want to show you the difference between, like, let's look at a high speed here. Like, here's a large speed, 1,500 meters per second. And you could see, if you go up to the other curve, that the higher temperature curve shows that you have a greater probability than the lower temperature curve. So that means that this high speed is much more probable at T2 than it is at T1. So 1,500 meters per second is much more likely at higher temperature than the lower temperature. And then if you look at like a low speed, let's say you're looking at 100 meters per second, right? Here's your two probabilities, say 100 meters per second. You have a higher probability at the lower speed, at the lower temperature, and a lower probability at the higher temperature. So molecules are more likely to be moving more slowly at a lower speed, okay? So for 100 meters per second, that's much more likely at the lower temperature than the higher temperature, okay? And I think that's all I really have to say about that. Again, this is something that you've probably seen before in general chem. I know I show my students this in general chemistry, and this is how the Maxwell-Boltzmann distribution of speeds varies according to molar mass. So as you go this way, the molar mass is going down, And that looks a lot like how it looks when the temperature goes up. In fact, it's really quite the same. What happens as the molar mass goes down is very much like as the temperature goes up. Okay, so you have greater average speeds for smaller molar masses, and you have a greater range, and all those same things I said are true here. Okay, so let me draw a little picture of that curve again. Here we go. Kind of a little more rounded than it really is, but I always have to draw these things several times. So this is your f of v versus v. And there are three different significant speeds to take note of. So over here, that would be the most probable speed. Okay, and then we have the average speed, which I guess I'll draw it over here. Put it in a different color. And then further to the right still, we have the root mean square speed. So I'll pretend it's over here. Okay, so these are not all the same. So why do they have this look to them? Well, most probable is just the height of the curve. That's obvious, right? At the top of the probability curve. So that's pretty understandable. Now the average is going to be shifted a little from the top because the average is when you have equal areas here. So you'd have this, because of the skewed shape, you have to be beyond the top of the curve to have those areas be equal. So the average speed has equal areas. Do you understand why they would be equal areas on each side? That average is when you have equal probabilities on being higher and being lower. Now, what about that v squared? You know, why is that higher? Why is that at a greater speed still? Okay. And, you know, that's just because of the property of squaring, right? So, I don't know, like, let's say you have two numbers. Like if you have 2 and you have 10, right? And you average them, that's 6. But if you take 2 squared, if you average the square and then take the square root of it, that's the root mean square, right? You take 2 squared plus 10 squared, so that's 4, and 100, that's 104. Now you'd have to divide that by 2, that's 52. And now that would be the average v squared. And then you take and divide that, and then you take the square root of that. That's a little more than 7. Maybe it's like 7.2. So this number is bigger than this number because squares, you know, it's a property of the square. Square goes up faster than a linear curve. So that's why your root mean square speed is higher as well. All right, so I think it's time for you to do something. So here's a problem, okay? Now maybe you've never done one like this. I don't know where you would have done one like this, but I'm going to show you how to do this problem. And it is a special problem, so you will, you know, you can submit your answer as usual. But then I have another special problem, which is for you to actually do the same thing, but for the root mean square speed. So this is a second special problem, but I'm going to show you how to do this first one and get you on your way with it. Okay, so what is this problem asking? So here's the Maxwell-Boltzmann distribution right there. And it's asking you to find the expression, find the expression for the average speed of a sample of gas molecules And this is the molar mass here. It's not molarity, okay? And at a particular temperature. So what integral would you have to set up to do this? And remember, when you're finding the average, right? The average of anything, like the average speed, okay? That would be the integral of the speed times the probability function, and you would integrate it all possible over all possible speeds. So this is what you have to figure out. So you have to set up the integral. So you would take your 4 pi m over 2 pi RT. That could be outside the integral. I might as well do it that way. And then I have my v here. And now I'm going to put my functional form in here, v squared e to the minus mv squared over 2 RT dv. So this is what I have to do. Notice that I have a v squared. This is from the distribution. This is from taking the average v. So you have to put that v in there. So that's what gives you a v cubed. So the integral that you actually have to do is v cubed e to the minus mv squared over 2 RT dv. Okay. Now, you know, this is not math class, and we don't spend a long time doing crazy integrals, which is why I give you what this integral equals. So here it is. It tells you that the integral of a variable cubed times e to the minus a constant, a is a constant, times that variable squared, dx, right, the variable is x, is 1 over 2a squared. Now let me write that down here. So this is what you're given. The integral of x cubed e to the minus ax squared dx is 1 over 2a squared. Now, you may not have to solve this integral because the bulk of the work is done here, but you have to figure out how to use it, all right? So that means you have to look at this, you know, look at that integral and figure out, you know, what's the a? Well, first of all, the x here, well, that's going to be v. That's pretty obvious. Doesn't matter what the variable is called. But the big part here is figuring out, okay, what is a here? Do I have an integral of the form e to the minus a squared? What, you know, what is a in our problem? So this is a question I'm really asking you.
Would it be the acceleration?
Now just tell me what constants it would be. I mean, here's your v squared, right? You need the coefficient of the thing that's being squared in the exponent.
The molar mass.
So molar mass over 2RT, right? Can't forget that, just because it's in the denominator. So, you know, when you're using an integral from a table, this is from an integral table, you can still make mistakes, you know, if you don't, you know, think about how to take your integral and cast it in the way that it's presented from the integral table, all right? So if a is equal to m over 2RT, then that makes this portion, this becomes e to the minus a v squared, right? So suddenly we have an integral of the form v cubed e to the minus a v squared, which is just like x cubed e to the minus a x squared. So what does that make this integral equal to? So let me continue in red because that's what I'm doing the calculation in. So I'll still carry down my constants. okay? But now this integral becomes 1 over 2 times a squared. So, and that a is m over 2RT. So this is actually the answer, right? But you can't just present it like that. You have to simplify it. Okay, so over here, 4 pi m over 2 pi RT to the 3/2. And then I'm going to flip this fraction here. So I'm going to have 2RT squared, right, over 2m squared. I think that's what it comes out to. Okay, and you still have to simplify it. It's still not, you want to cancel everything that you can. All right, so I'm not going to do the whole thing for you, but I'm going to tell you the approach that I would take. This m over 2 pi RT to the 3/2, I know that the 3/2 power is m times n to the half, and I have to do that to everything. I would make it m to the half over 2 to the half, pi to the half, r to the half, t to the half, because that just makes it easy to cancel. I've had students who like to keep track of the exponents and have it be a different fraction. Yeah, that's fine. But you got to show me all your work, and you should do it right. So this is, and already I made a mistake because this is not 2RT squared. It's 2RT all squared because this whole thing is squared. So I have 2 times 2 times r times t over 2m squared. So that's m times m. And then that allows you to do some canceling very easily. So I would like you're going to do the answer here. And you should see that the number that you get, I'll actually give you the answer. It's the square root of 8RT over m. And that's the average speed. Okay. And so you're going to finish this. Finish this is the special problem on the average speed. And then the second one I'd like you to do is the root mean square speed. But before I just want to show you, so you're going to be, when you look at 8RT over pi m, and 3RT over m. So this is a root mean square speed, and this is the average speed. And remember, I told you the root mean square speed was going to be higher. So how does 8 over pi compare to 3? Right, 8 over pi is about 2.5, and compared to 3. So this is a little bit smaller than this is. So that's the one on the average speed. And then the next problem is to do the same thing. Use the same distribution function, but this time you're going to find the root mean square speed. So you're going to find the average of the v squared using this integral that I give you. And then at the end, you'll take the square root of it. Okay, and you should get this form that you know. So at least you know when you've got the right answer. Okay. Okay, so that's another special problem. That's on Blackboard. I have you post them together. So I think I put down Thursday for it or something. All right, so I have just a few minutes, like maybe 15 minutes to start talking about the next topic for the class, which is that gases are not always ideal. All right. So we're going to talk a little bit about real gases. Okay. So I'm going to, we'll talk about what is the evidence for this, and when does it occur? In other words, what conditions that gases aren't ideal. And we're going to talk about whether you can predict this, whether there are any other equations of state, right? Remember how we talked about the ideal gas law as giving you an equation, and every state of an ideal gas satisfies that equation. Is there any other equation that works for non-ideal gases that may be used to describe this behavior? So the first thing I'd like to talk about is, when does this occur? Under what conditions? And, basically the ultimate evidence of gases not being ideal, the ultimate consequence is liquefaction. Okay, if there weren't any liquids, we wouldn't have non-ideal gases. But when do liquids form? They form at low temperatures, and they can form at high pressures as well. Okay, so in both of these cases, right, gases have smaller molar volumes, right, because volume is proportional to temperature. So, and when you have high pressure, you also have small volume of 1 mole. So we say small molar volume. And this also, you have small molar volumes. And so when you have gases that are in a smaller volume for 1 mole, what happens is that you get interactions between the molecules. Okay, so gas molecules do interact with each other when they are close enough, and it leads to things like liquids forming. Okay, and the particular kind of interactions that happen between gas molecules depend on how far apart they are. Okay, so we have like 3 different sort of ranges, 3 different realms. We have basically the low pressure realm. And when gases are at low pressures, there are no interactions, right? Because the molar volume, that's what this Vm is large. And so they're too far apart. And you know that the ideal gas law is what we call a limiting law. So it is always ideal on the limit of low pressure. So at low pressures, we have no interactions, and the gases really behave ideally. But when you start to get up there, so you start to get moderate pressures, I'm going to call them, then what happens is that you get attractions. And these attractions depend on the kind of intermolecular forces that you have in that particular compound. Like you could have dipole-dipole, or you could have hydrogen bonding, or you can have dispersion forces in any gas, as long as they're close enough. Okay, so you're going to start to get some attractive interactions at these moderate pressures. And then we have the high pressure situation, where here now gas molecules are maybe trying to occupy the same space. Okay, so this leads to repulsive forces. So this is like, get out of my space, so gas molecules repel when they're at very close range. So you can imagine that first their electron clouds start to overlap, but as they get closer, then you'd even get nuclear kind of repulsions kind of forces. So that's what happens at high pressure. We'll talk more about that later. Let's think about these attractions. This is what happens at moderate pressures. Deal with that first. So if I have gas molecules moving in a container, and let's say this molecule here is heading for the wall. Okay, that's what causes pressures, it's collisions with the walls. So if we focus on this one molecule and it's about to hit the wall, but it's got a few neighbors around it, right? And it's attracted to those neighbors. And so what happens is it hits the wall less frequently and with a smaller force. So basically the neighboring molecules pull this molecule away from the wall. So the number of collisions per second goes down and the force per collision goes down. And both of these lead to a pressure that is lower than the ideal gas law would predict. So in this moderate pressure range, P is less than P ideal. And that simply means that the pressure is less than what the ideal gas law would predict. So P is less than nRT over V, because that's what the ideal gas law predicts. So what we do is we find this ratio. We take the pressure, the actual pressure over the ideal pressure. Okay, so we call it P over P ideal. And that's P over nRT over V. So that's actually PV over nRT. And we know that P is less than P ideal. So P over P ideal is less than 1. So this will be less than 1. And we call this the compression factor, or the compressibility. So P over P ideal is another way of writing this Z, the compression factor. So P over P ideal is equal to PV over nRT, right? What would PV over nRT equal for an ideal gas, right? If a gas is ideal, PV equals nRT. So PV over nRT is equal to 1, right? So that means, and this is P over P ideal, right? Because it's P over nRT over V, PV over nRT. So this would mean that P is equal to P ideal. Okay. So, but when it's not, when there are attractions, then this PV product divided by nRT is actually going to be a number that's smaller than 1. So, so that's one thing that happens. That happens at moderate pressures when there are attractions between molecules. Yeah. So why do we call it the compression factor? Well, because it allows us to distinguish between when the pressure is less than the ideal pressure and when it's greater than the ideal pressure. So when molecules are attracting each other, the pressure is less than the ideal pressure. When molecules are repelling each other, the pressure becomes greater than the ideal pressure, and the Z becomes greater than 1. But let's stick with this for a while. So when Z is less than 1, the gas is more compressible. And it's very simple why it's more compressible. It's more compressible because it has a lower pressure. The lower pressure, the easier it is to compress. Okay, so P is less than P ideal. It's smaller, so it's easier to compress. Okay. All right, I think that's next time. I'm going to start with this table here. Let's see. I'll show you, so if you want to look at it before you come to class. I have this, this is some data for, so what this is showing is what the pressure is, what the measured volume is, okay? And it does this from a range of very low pressure to extremely high pressure. So you can see, you're going to calculate what the ideal pressure is. You know what the actual pressure is because that's just the pressure. And then you'll take the ratio and you'll see what happens to Z as you go from low to high pressures. Z changes a lot because when you start out, Z is going to equal 1 because you have an ideal gas at a low pressure. As you start to increase the pressure, you're going to get more attractions. But eventually, as the pressure gets really, really high, you're going to get repulsion. So you're going to go from the gas being more compressible, going from ideal to more compressible than ideal to a whole lot less compressible than ideal, with that gas fighting back. It doesn't want to, it's like two molecules trying to take up the same room. So that's what we're going to start with next time. I don't think it pays to start right now with it. We'll do that next class. Okay. Questions? So some of you I will see in a little while. All right, good. Bye.
Thank you.
Thank you.
Thanks, everybody.
If anyone has a question, you can hang around.